Figured I'd start off by writing the problem down because it takes like 5 minutes to write the problem down. So, if anybody doesn't know me, my name is Jake Shozer. I'm a brother in Sigma Phi Epsilon. I'm a 4 out of 5 Mechie. My name and email is right up there. This is part 2 of the lovely 3-part differential equations review sessions. And tonight's going to be all PDEs. The thing that we have come to know and love, mostly hate, but I'm going to call it love. We have this, it's very simple what they're going to give you. They're going to give you either a heat equation or a wave equation. So right here, this is a heat equation. We know that because the U of t has, it's just one t right here. And then we have some constant u double x. The only difference that they could give you is they can make this 2 t's and they can change that number. That's the only difference in this part. Then the boundary conditions, initial conditions, they can give you basically whatever they want. But this part is basically the same for one versus the other. So tonight what we're going to do is we're going to go through this problem. And then I have a wave equation, which is pretty similar, but it'll just be more practice for us. So I'll solve this one, we'll solve the wave equation, and then we'll all go home and go to sleep. And then if anybody wants to come back tomorrow, not the same place, but the same time. So tomorrow it's in Kitty 228 at 9 p.m. It's going to be part 3 of the review session. And I'm doing something a little different this time, where I'm going to do just, you guys bring me questions. So if you guys have any problems from previous tests from this semester that you don't know how to solve, I'll answer them. If you guys want to come and just do practice problems in your seats and like raise your hand, call me over to help you out when you get stuck, we can do that. It's basically just going to be whatever you guys want, I'll be ready to help you guys out with. I'm not going to have any questions prepared or whatever, but again, whatever you need, I'll help out with. And then you guys have all day Wednesday to prepare yourselves for the torture on Thursday. Does it sound like a plan? So I also want to give a nice shout out to SITTV again for 2 days in a row coming out recording this, so that way you guys can watch it back and anybody who wasn't here can watch it again. So that way, and then even for future semesters, because I'm sure I'm going to send this link out in a future semester. So to those people watching it, you're welcome, and thank you to SITTV. So, are there any questions before we get going with our heat equation? Seeing no hands. So what makes the heat equation, all these partial differential equations, so much fun is because it's not just one question. You only see one question, but it's really like 2.5, sometimes 3, all wrapped up into one, which is just great. So the first step of these questions is you get to do an entire separation of variables question. So you start off with this, you do all your separation of variables, and you get to an answer. And then you use that answer, and that is the starting point of an eigenvalue problem. And then you get to do case 1, case 2, case 3 of an eigenvalue problem. And then you get your answer from that. And then if they're nice to you, you can kind of just do some playing around with your end values to find your initial conditions. But if they're really mean, then the end of your eigenvalue problem is the start of a Fourier series problem. I don't think they're going to give that to you on the final, but I know I had seen it on like a homework or a gate in a previous year, and that was just torture. The way that you would know if you had to do a Fourier series in the last part is this initial condition would look a little bit different. The initial condition would actually look like a series, whereas right here we just have a couple terms written out. So odds are you're going to get something closer to this, which will make that third part a little bit easier. So, like I said, the very first thing that we get to do is we get to do a separation of variables problem. So I know that if I was given this in separation of variables, where my u is a function of capital X and capital T, I know that if I have u sub t, that just means I take the derivative with respect to t once. So this left side is just going to be capital X, capital T prime. And that's going to be equal to 3 times capital X double prime t. Again, because this just means partial derivative with respect to t, and second partial derivative with respect to x, which is what we have here. And from this point, it should look pretty similar to some of the other some of the other partial or separation of variables problems that you guys had. I think you had one on test 3. So the first thing that we want to do is we want to separate the variables. We want to get all of our x's on one side, all of our t's on the other. So what I'm going to do is I'm going to divide by capital X on both sides. So that way this goes away. And then I'm also going to divide by capital T. So that way this goes away. And what that leaves me with is capital T prime over capital T is equal to 3 capital X double prime over capital X. And does anybody remember what we do at this step? Yeah.
Set equal to negative lambda.
Set equal to negative lambda. What a wonderful thing, because I mean, when you're just doing separation of variables, that didn't seem too difficult. Oh, we're just throwing a number in there. But this is the lambda that makes you have to do Eigen Values. It's all coming full circle now. So we now have this negative lambda, and we can split it up into 2 different ordinary differential equations, in which case we're only going to have t's in one of them, and we'll have only x's in the other. So let's break this up. I'm going to just look at this part and this part. So I'm going to have t prime over t is equal to negative lambda. And I want to get this to look like an equation that I've been used to solving all year. So I'm going to multiply this t to the other side, and then I'm going to add that whole thing back over. So this is just going to be t prime plus lambda times t is equal to 0. And then I do it with my x's. I'm going to have 3x double prime over x is equal to negative lambda. So again, I'm going to multiply this x over, and then add this negative lambda x back to the left side. So it's going to leave me with 3x double prime plus lambda x is equal to 0. So now if you notice here, this is just a first order ordinary differential equation, and this is a second order ordinary differential equation. So one thing that I want to do just to save us a little bit of time, do I do that? To save us a little bit of effort when we're solving this, is I'm just going to divide both of these terms by 3, just so that way I can have, instead of having the 3 in front of my double derivative, I'd rather have it in front of just a single term. So I'm going to divide everything by 3 and make this a 1/3. Because this is something I'm a little bit more used to seeing. So now if this was just a separation of variables problem, I would take this, or I would solve this, and multiply them together, and I would get my answer. So let's try and do that. First, we're going to take the term with just the t prime. Let's go to black. So now I'm going to solve these 2 equations that I got. Hopefully I'll get some function for t, some function for x, which I can then multiply together to get my function u, which is what I'm trying to solve for in this whole problem. So I have t prime plus lambda t is equal to 0. So I know that the first thing that I need to do, this is just a homogeneous equation. I can just set up my auxiliary. So I have m plus lambda is equal to 0, which means that m is equal to negative lambda, which tells me that my capital T function is just going to be equal to some c1 times e to the negative lambda lowercase t. So I'm halfway done. This still seems pretty simple so far. Now I get to my second term, where I have x double prime plus 1/3 lambda times capital X is equal to 0. And now again, I'm just going to try and solve this like a second order differential equation that we've been doing all year. So I'm going to set up my auxiliary equation, where I have m² plus 1/3 lambda is equal to 0. I'm going to move this over, so I'm going to have m squared is equal to negative 1/3 of lambda. I take the square root. I'm going to get m is equal to plus or minus the square root of negative 1/3 lambda. So now I have my roots, but we face an issue. Because I know that back when I was solving for my roots, way back in the end of test 2, I know that if I got roots that were real roots and they were not the same, I would have one form of a homogeneous answer. I also know that if I had real roots that were both the same, I would have a different form of my answer. And then if I had imaginary roots, I would have a third form of the answer. So we need to figure out right now, is this real repeating roots? Is it real non-repeating, or is it imaginary? So we have to look at this and say, okay, if this whole thing that's underneath this radical, this negative 1/3 lambda, if that is equal to a positive number, because we don't know what lambda is, if this is a positive number, we take the square root of a positive number, and we get plus or minus that positive number, which is going to be 2 real non-repeating roots, which would give us one situation. And that situation was when we had negative 1/3 being some positive value. Well, what if lambda ended up being 0? If lambda was 0, then we know our negative 1/3 lambda would be equal to 0. We would get plus or minus 0, and we would have real repeating roots. That would be a different case. Now another situation is, what if this whole negative 1/3 lambda ended up being less than 0? Well, if it's less than 0, then we have a negative number underneath a square root, which means we have imaginary. And we don't know what lambda is. So we have to test all 3 situations, which is where our eigenvalues come into play. So I'm going to go to, can you guys see the orange? No, I'm getting hard nose from the back. Okay, so we're going to go back to black. My markers are starting to die out at the end of the year. What? I mean, I have a bunch. I'm just going to rotate through them all. But thank you. So, we now do our eigenvalues. And the first thing that I'm going to do for case 1 is I like to say, in case 1, what if this is true? What if the whole thing underneath that radical is equal to 0? So I'm going to say that negative 1/3 lambda is equal to 0, which means that lambda is equal to 0. If that's the case, then I know I'm going to have m equal to plus or minus the square root of 0, which means that m is equal to 0. And if m is equal to 0, I know that my homogeneous solution is going to be capital X, because that's the function we're dealing with, is equal to C1 e to the 0x, so just C1 plus C2x times e to the 0x. So this is what my answer would look like. Now we need to check if this is a possible answer by looking at our boundary conditions that it gives us. Because I'm saying that if this is true, then that has to be true. Let's check to see if it's possible given the conditions that the problem tells us are true. So this problem gives us our boundary conditions as u sub x when we have x equal to 0 and t equal to t. And over here we have x equal to 4 and again t equal to t. So what this is telling me is that t doesn't matter at all. I mean, I solved for t already, and I can write out a full function for u at this point, but it's just going to put more terms in there that are going to confuse me. I only need to worry about the fact that I have to take the derivative with respect to x and plug in 0 for x. I don't have to worry about t yet. So I can just have my condition of taking the derivative of this gives us x prime is equal to c2. So now I have x prime equal to c2, and I can plug in that first boundary condition, where it's u sub x when x is 0 and t is t. And it says that it's going to be equal to 0. And if you notice, I'm not even plugging in anything. I'm not even ending up plugging in this value because I have no variable x's. I don't have no lowercase x's in my function. It's just capital X prime is equal to C2. And that's all the information that I get. So now I try and plug in my second condition, which is the partial derivative of u with respect to x at 4 is equal to 0. But I'm just going to get the same exact thing because I have nowhere to plug in the 4. So out of all of this, I just get that 0 or C2 is equal to 0. So when I plug that back in here, that tells me that x is equal to C1 because I found out nothing from C1. So what this tells me is I do have a solution. I have a constant solution in this case 1, which does happen every once in a while. So I have to write this out as xn cn because it could be any constant, so we write it as infinitely many terms with the sub n. And I know that this right here are my eigenfunctions. And what this is telling me is that if this lambda were to be 0, so if I took 0 and I plugged it in right here, then I could have any constant plugged in for my x, and the equation would be true. So that's my answer from case 1. Now we move on to case 2. So for case 2, we're going to say that everything underneath that radical is going to be positive. So this one is going to be our case 2. So for case 2, we say that negative 1/3 lambda is positive, which means that I'm going to set negative 1/3 lambda equal to alpha squared. Because pick any number for alpha, if you square it, it's going to be positive no matter what. So if that's true, then I can plug in this alpha squared for my 1/3, not my negative 1/3 lambda, which is going to give me m is equal to plus or minus the square root of alpha squared, which means that m is equal to plus or minus alpha. And in this case, I have real roots, and they are non-repeating. So I have positive alpha and I have negative alpha. So I can have my homogeneous solution be capital X is equal to C1 e to the positive alpha little x plus C2 e to the negative alpha times little x. And just like I did over here, after I found my homogeneous solution, I took the derivative, plugged in my boundary conditions, and went on from there. So let's do that. Let's find our derivative. So x prime is going to be equal to, we're going to have C1 e to the alpha x, because the derivative of e to the alpha x is just e to the alpha x. But then we have to take the derivative of the exponent, which is just going to be alpha, to account for the chain rule. And then the second term is going to be minus alpha C2 e to the minus alpha x. And now I can plug in my boundary conditions. So I have my x prime term, and I'm going to plug in 0 for x in that first condition. And I know that when x is 0, my x prime is also 0. So I have 0 is equal to alpha c1 e to the 0 minus alpha c2 e to the 0. So these e to the 0s both become 1, so they can go away. And I'm going to move this over, so I have alpha c1 is equal to alpha c2, which tells me that c1 is equal to c2. Now I'm going to plug in my second condition. And my second condition is when x prime is equal to 0, my x is equal to 4. So I have 0 is equal to alpha c1 e to the 4 alpha minus alpha c2 e to the negative 4 alpha. Now I'm going to move one of these over to the other side. Have alpha c1 e to the 4 alpha is equal to alpha c2 e to the negative 4 alpha. I know that alpha can't be 0 because if alpha is 0, that means this whole term is 0, and that brings me back to case 1. So alpha can divide out. And I know that c1 is equal to c2 because that's what I found out right here. So I can divide out these terms. And I'm left with e to the 4 alpha is equal to e to the negative 4 alpha. Which, no matter what you plug in for alpha, that can never be true. Because I can never have e to a positive exponent is going to be a big number. E to a negative exponent is going to be a small positive number. There's no way I can ever make these two sides equal.
What about when alpha is equal to 0?
If alpha is equal to 0, then we're no longer in case 2. That brings us back into case 1, because then our negative 1/3 lambda would be equal to 0. So we know alpha can't be 0, so we know that that's not a true statement. And in this case, we have no eigenvalues. And this should look familiar, because most of the time in case 2, you get to this point where you have something equals something. It's not true. You write no eigenvalues. Now the fun one. Case 3. In case 3, I'm going to say that my negative 1/3 lambda is a negative number. So it's less than 0. And if it's less than 0, then I know then I can set it, I can do this negative 1/3 lambda is equal to a negative alpha squared. Because again, no matter what number I choose for alpha, when I square it, it's going to be positive. So if I throw a negative in front of it, it's negative. So now I can take this negative alpha squared and plug it in for in my m equation over here. And I'm going to get m is equal to plus or minus the square root of negative alpha squared, which gives me m is equal to plus or minus alpha I. So again, keeping forward with the same steps, we have capital X, writing out our homogeneous solution. Capital X is equal to, it's going to be e to the 0x times c1 cosine of alpha x plus c2 sine of alpha x. Because we have 0 in front of our plus or minus, so we have e to the 0x. And we have an alpha in front of our imaginary term, so we throw our alphas inside our sine and cosine. So just like we did in case 1 and case 2, now we're going to take the derivative, and then we're going to plug in our boundary values. So the derivative of this, because I know that that's just going to go to 1, so I can ignore it. we have x prime is equal to negative c1 sine of alpha x. And then we have to take the derivative of inside the parentheses, so it's going to be negative alpha c1 sine of alpha x plus alpha c2 cosine of alpha x. Now I plug in my boundary conditions. I'm going to plug in 0 for x prime, and I'm going to plug in 0 for x. So I'm going to have 0 is equal to negative alpha times c1 sine of 0 plus alpha c2 cosine of 0. I know that sine of 0 is just 0, so that goes away. I know cosine of 0 is 1, so I'm left with 0 is equal to alpha c2. And again, we know that alpha can't be 0, so we have 0 equals c2. Yes?
Can you explain why you crossed out e to the alpha?
Because we have e to the 0x, so anything to the 0 power is just 1. So this just becomes 1, and I have 1 times this whole thing, which is just that whole thing.
When we did case 1, why did we plug in the second, like, BC to case 1 we did?
So we did and we didn't. If I were to try and plug in the second boundary condition, I still have my derivative as x prime is equal to c2. It tells me that my u of x, so my x prime is equal to 0. And when I plug in 4, there's nowhere to plug in the 4. So it's the same thing for both of them. So we did, but we didn't. Cool. So we now have that 0 is equal to c2. So now we can go through with plugging in our second boundary condition, and hopefully we get a value for c1. Otherwise, we just wasted a lot of time. So now, plugging in our second boundary condition, I'm going to say that 0 is equal to we're going to have negative alpha c1 sine of 4 alpha plus alpha times 0, so I know that c2 is equal to 0, cosine of 4 alpha. So this whole second term goes away because it's being multiplied by 0. So all I'm left with is negative alpha c1 sine of 4 alpha. Now, I know that alpha can't be 0 because then we would be back in case 1. So if alpha can't be 0, we don't want c1 to be 0 because if c1 is equal to 0, we again have no solution. So I want to say that 0 is equal to the sine of 4 alpha. Right? Because in order to have this thing all of these terms multiplied together to be 0, I know only one of them needs to be 0. So I'm going to say that sine of 4 alpha is equal to 0. Now we need to figure out what needs to go inside these parentheses. What does 4 alpha need to equal in order for this to be true? So I go to my unit circle. And on my unit circle, I know that sine is the y value. And at what points on this circle is my y value equal to 0? Well, I know right here, my angle right here is 0. Then I move around the circle and I get right here, and my angle's pi. And then I keep moving around the circle and I get 2 pi. And I get 3 pi. And I get 4 pi and 5 pi and 6 pi. So I know that as long as whatever sine of something, if this something is a multiple of pi, I know that it's going to equal 0. So the way that I'm going to represent this multiple of pi is with just the letter n. And I'm going to say that n can equal 0, 1, 2, and so on. So I know that sine of n pi is equal to 0, and 0 is equal to sine of 4 alpha. So I can then make this statement and say that 4 alpha has to be equal to n pi. Does that make sense? Hopefully it does. Now the whole purpose of this is we're trying to figure out what alpha is so we can then use alpha to figure out what lambda is. So if I want to solve for alpha, this one's not too difficult of a situation. I can just divide over this 4, and I'm left with alpha is equal to n pi over 4. But I don't really care what alpha is, I care what lambda is. So I'm going to take this, plug it in for my alpha, where I have negative 1/3 lambda is equal to negative n pi over 4 squared. I can divide out these negatives in front, and I can multiply this 3 over to the other side. And I get that my lambda, and I'm going to write this as lambda sub n, just because I had an n on this right side. So lambda sub n is equal to 3 times n pi over 4 squared. 4, n is equal to 0, 1, 2, dot, dot, dot. And what this represents is all of my eigenvalues. And a question like this is going to say, find all of your eigenvalues and eigenfunctions. So our eigenfunctions is basically the answer to this problem. We want the function that's the answer, which is this c1 cosine of alpha x plus c2 sine of alpha x. Well, I know that c2 is 0, so I don't have to worry about that term. And I know that alpha is n pi over 4, so I can just plug into this what I know, and I get that x is equal to c1 cosine of n pi over 4 times x. And again, I'm going to write x sub n, and for n is equal to 0, 1, 2, dot, dot, dot. And what this represents is all of your eigenfunctions. Yes?
Do you leave it as C of 1, or do you turn it to C of n?
Yeah, it should be C of n. Just because it's going to be different for each value of n. So now, does anyone want to take a shot and explain to me what an eigenvalue and an eigenfunction actually even means? Because they probably explained it right at the beginning of the unit when you had absolutely no clue what was going on. And then at the end of the unit, when you had a slight clue what was going on, they never mentioned it again, and you just have no clue what it actually means. Do I need to we're good? Okay, cool. So, what an eigenvalue and an eigenfunction is, let's trace this back to all the way where we started. We said that if this negative 1/3 lambda is any negative value, like this whole thing comes out to be a negative value, what would my answer look like? My answer would look like this. Now we're going to get a little bit more specific. We're going to say, what values can lambda specifically be to make this problem work out? Well, these are the values that lambda can specifically be. If I plug in a 0 for n, if I plug in a 1 for n, or a 2 for n, or a 3 for n, these are all of the values that I can plug in to this lambda to make this problem make sense, to make those boundary conditions true. And if I were to take, say I plug in n equals 1 for lambda into this problem, or even all the way back to this problem, I plug in n equals 1, take that lambda, plug it in here, and then solve it like a normal problem, the answer that I would get would be this, just if I plugged in 1 for that n. And if we had enough time right here, right now, I would actually prove it to you and show you that if I plugged in 1 here, I would get that out as my answer with that n being a 1. You can try it on your own, or I can do it after if you guys want to stay after we're done with the review. But that's what eigenvalues and eigenfunctions are. You take this, plug it into the original problem, that's your answer. Okay. So we're 2/3 of the way done with the problem now. We did all of our separation. We got our answer from that, which was this and this. We solved this. We did a lot of stuff with case 1, case 2, case 3, and we ended up getting, we did get a constant solution in our first one, but this is the one that really matters. The last thing that we need to do is we need to actually figure out what our u term is. We want to figure out what happens when we multiply x and t together and apply that initial condition of u at x and 0. So let's do that last step. I planned this out poorly with my boards, normally better than that. So I'm going to erase case 2. So now for the first time, I'm going to write out what my u is. So my u of x and t is going to be equal to, I'm going to take that function x, so I have c sub n cosine of n pi over 4 times little x, and then I'm going to bring in this ce to the negative lambda t. I'm just going to write it as e to the negative lambda t, because this coefficient kind of absorbs the other one. So I now have this as my answer, and I'm almost done. Yes?
How did you get that?
I took my capital X, which I found right here, which is c sub n cosine of n pi over 4 x, and I multiplied it by my capital T, which I found all the way back here like 20 minutes ago. Yes?
Did you ever have to do like eigenvalues for both?
The only time you might have to is in a wave equation, but they're probably not going to have you do eigenvalues for both. They'll make it so that way this one you can solve without eigenvalues. Yes? You're saying this one? You could, but it's not really a fun answer, because then this, all that you would have would just be c sub n e to the negative lambda t. And actually, I think you end up getting the same answers anyway. Kind of. Well, actually, no, because your initial conditions have these cosine terms in here. So if you didn't have your cosine from that x sub n, then it wouldn't be in there. So this you need to show because they like to see it, but you don't really care about this end. You never do. You always care about case 3. Okay. So now we got to do that last step of plugging in. Is that a question? Oh, sorry, my bad. In case 3, where did my what term go? E, because it's e to the 0x. The reason why it's 0, in any problem that you do, it should be 0, is because right here, it's m equals 0 plus or minus alpha I. And that 0 becomes the exponent there. So now we're here. For the first time, we actually have written out our entire function of u, which is our capital X that we found here and our capital T that we found all the way over here. So the last piece of the problem that we haven't used is that initial condition, which is that bottom line. And what that's telling me is that my initial condition, so when I plug in 0 for t, I should get cosine of pi x over 2 minus 7 cosine of 3 pi over 4x plus 5 cosine of 3 pi over 2x. Now that seems really complicated. But what that's explaining is, right now what we have written down is in terms of n. So this equation is valid for any value of n that's 0, 1, 2, 3, 4, 5, 6, 7, all the way up. What this is telling us is that we only 3 of those terms are valid for this initial condition. So our goal is basically to figure out what value of n corresponds to this first term, what value of n corresponds to the second term, and what value of n corresponds to the third term. So we're going to plug in 0 for t, because that's what this initial condition tells us to do. And then we're going to see what values of n we can get. So u of x comma 0 is going to be c sub n cosine of n pi over 4x times e to the 0, which is just going to be 1, and we don't need to write it. So I now know that c sub n, and again, this is still, this side we still can use any value of n, is going to be equal to cosine of pi x over 2 plus or minus 7 cosine of 3 pi over 4x plus 5 cosine of 3 pi over 2x. And like I said, our goal right now is to figure out what value of n can we plug in here that it makes each one of these true. So for this first one, I see that inside these parentheses, this is n pi over 4x. And here I have just pi over 2x. So I know that that tells me that n is equal to 2. Right? Because I plug in 2 there, I'm going to get 2 divided by 4, which is 1 over 2. 1 over 2 pi x. And since I know that this is n over n equals 2, I know that c sub 2, my coefficient when n equals 2, is just 1. Because that's what I have out in front here. Now I can do the same thing for this next term. What value of n do I plug in here to give me 3 pi over 4? N equals 3. Because I'd have 3 pi over 4x, which is what's inside these parentheses. And in this case, c sub 3 is negative 7. And then the last one, we have n equals 6, because if we have 6 over 4, that's going to give us the same thing as 3 over 2. And our c sub 6 is equal to 5. So just like in all the problems that you've been doing all year, when you're given initial conditions, it helps you find your coefficient. So normally it's just C1 and C2. But in this case, we have C1, C2, C3, C4, C5, 6, 7, 8, 9. But what this tells us is that C1 is equal to 0, C4 is equal to 0, C5 is equal to 0, C7 is 0, C8 0, and all the other C's are 0. The only ones that we care about are these three. So now we can take this, along with knowing what our n is, plug it back in up here, replacing our value of lambda with n equals 2, n equals 3, and n equals 6 for what we found for lambda up there, and we're going to have a final answer. We're almost there. So here's what we got to do. We're going to say that u of x and t is equal to, I'm going to start with my n equals 2 term. So when n equals 2, I know that my c sub n is equal to 1. Then I have cosine of n, which is 2 pi over 4 times x, e to the negative lambda times t. But I know that lambda, if you look up there, is going to be 3 times 2 pi over 4 squared. Now you can simplify this a little bit, but instead of having 2 over 4, you can just make this a 1 over 2. So that's what I'm going to do right now. So we have 1 over 2 inside of our cosine, and we have 1 over 2 in this exponent. Keeping our pi's there. So now this whole thing corresponds to my n equals 2 term. Now I need to do the same thing for n equals 3 and n equals 6. So plus c sub n, I know is going to be negative 7. So we have minus 7 cosine of n, which is 3 pi over 4 times x, times e to the negative lambda, where lambda is now 3 times 3 pi over 4 squared times t. And this whole thing is my n equals 3 term. Almost there. Got one last one. Our c sub 6 is going to be 5. Then we get cosine of 6 pi over 4x times e to the negative 3 times 6 pi over 4 squared times t. This is all our n equals 6 term. And again, you can simplify the 6 over 4 to just be 3 over 2. And this monstrous answer that takes up the entire board is your solution to this partial differential equation with these boundary conditions and that initial condition. So that took us about 50 minutes for one problem. On the test, it's probably going to take you just as long, if not longer, but that's why it's only on the final.
So that's what the answer looks like that's its own.
This is, you put a box, I'm not going to waste my markers, but you put a box around that. I mean, you can get rid of this one in the front. You put a box around that and you're done.
What would you absolutely use for?
So if you had to use Fourier series, and I haven't seen one of those problems in a while, but you would have, this initial condition would be different. This would be given to you as a series, not as multiple terms added together. Yeah, it's really weird. I don't think they've ever given it on the final, just because like I did one example in this review last semester, and even I had no clue what was going on. It just went downhill fast. So I don't think they're going to do that to you on the final. Yes. Say that again? Lambda is up there. Because we found that lambda is equal to this, so we take n equals 2, we plug it into lambda, and we get that. We take n equals 3, we plug it in, get that. We take n equals 6, plug it in, get that. So this is an entire heat equation problem. Now you're going to have either a heat equation or a wave equation on the test. And if I had to guess, which I've gotten pretty good at for this class, I'm going to guess that you're going to have a heat equation. The reason being, for like 3 or 4 years in a row, they gave a heat equation. Last semester, they changed it up and gave the wave. But, so people would think, oh, maybe they're going with a string of waves. No. In the review that the math department did yesterday, they did a wave equation. So they're not going to do the wave equation, then give you the wave equation. They did the example of the wave equation, they're going to give you the heat equation. Now, if I'm wrong, you can't blame me. But it's a very similar problem one way or the other. But my guess is that the only difference when you're actually doing the wave equation versus a heat equation, which we're going to do the wave equation next, is for the wave you have a second initial condition. And it's a nice simple initial condition. The reason why you need that is because you have a second derivative here and a second derivative here. So we have 2 boundary conditions because of the 2 first derivatives. We only have 1 initial condition, so we only have 1 second derivative. When we have the second derivative, we need a second initial condition. I know that's a lot of words, probably confuse a lot of people. Are there any questions on heat equation? Yeah.
Will they tell us if they need a wave equation?
No. The way that you'll know, if this t is just a single derivative, it's heat. If it's 2 derivatives, it's wave. And honestly, it doesn't matter in solving the problem. It's the same steps one way or the other. So if there's no questions on heat equation, I'm going to take like 5 minutes to erase like all of the boards. You guys can take a quick mental break, and then we'll come back in like 5 minutes and we'll do some waves.
Jake, this is kind of just a question.
Yeah.
So what's the difference between capitalized and lowercase?
The capital is the function. So like normally we're dealing with y as our function and x as our variable. Well, right now we could have x and y as both functions. Or in this case we have capital X and capital T are both functions. Lowercase x and lowercase t are the variables. So think of your capitalized as your y and your lowercase as your x.
All right, I was just wondering. It's like in my eyes, it's just like, would they take points off if they like switched it so you didn't like get confused?
You're not really going to take points off. They probably won't take points off if you just like write an x too big, but you're more likely to confuse yourself by writing it too big, which will get you a lot of points off because you're messing with the impact problem.
Yeah. Okay. Thanks, man.
No problem. get to the end, you have to plug in 1 4. So I figure I'll do both. No, I'm just wondering. All of the steps. Okay, so now we got our wave equation, which is written on the board. And notice this one's written a little differently, where it's showing double x minus u of double t is equal to 0. Our first step is we're just going to move it over, so that way we don't get confused that there's a minus and an equals is 0. But like I said, the only real difference in this one, they changed the constant. It was a 3 in the last problem, now it's a 16. And now our t has a second derivative, where in the last problem, we had the second derivative in the x, but only one derivative in the t. Now we have double for both of them, which is going to add a little bit more complexity to it, but not too terrible. Yes?
When they give these questions on the test, will they say like boundary condition like BC and then give like equations, or will they just have something?
I believe that they do list like boundary condition, initial condition. I'm not positive though, but I would think that they do. Yeah. And then aside from the fact that we have our second derivative for our t, the other thing to note is we have a second initial condition, which we need that second initial condition to be able to figure out our second constant that we're going to have in this problem. But you notice that it's a pretty simple condition where it's just plug in 0 for t and you get 0 out. So, are we ready for this?
No.
Okay, then we can just leave. Okay, so this one I'm going to go a little bit quicker in the beginning steps just because it's the same process that we just did. But then once we get to the actual stuff that makes this different, I'll slow it down and explain a little bit more. So, first things first is I'm going to move that negative 16 u double t to the right side. So we're going to have u with the second derivative with respect to x is going to be equal to 16 u double t. And now if you look back in the notes that I have for solving separation of variables, first step, write it out in terms of the capital X and capital T. So we're going to have capital X double prime times t is equal to 16 times x t double prime. Next thing that I'm going to do, somebody say anything? Nope, okay. So we're going to divide by capital X, capital T. And our t's are going to go away. Our x's are going to go away. And then one thing that will make a later step of the problem a little bit easier, I'm also going to divide this 16. You don't have to do it. In the last problem we didn't do it, but it's going to make it just a tad bit easier in the end. Because what we're left with once we do all that is we have x double prime over 16x is equal to t double prime over t. And in comes our lovely lambda. When we get to this step, we set up our two ordinary differential equations, which in this case, we're going to have x double prime, take this 16x, multiply it over, and then add it. So it's going to be plus 16x is equal to 0. And then we're going to have t double prime plus, I forgot the lambda. Not bad. So it's going to be 16 lambda x is equal to 0. And then here we're going to have t double prime plus lambda t is equal to 0. So we're going to look at this one first. And for this one, we're going to have our m squared plus 16 lambda is equal to 0. 16 lambda m. Right? No, not m, not m. I lied. Which means this is m squared is equal to negative 16 lambda. Take the square root of both sides, and we have m is equal to plus or minus I'm going to pull out this negative 16, make it 4i. So we're going to have 4i times the square root of lambda. Now this one I haven't solved myself, so I'm actually going through it for the first time now. So it might take a little bit for me to think, so I got to make sure. But I don't want to do that because lambda could be negative. So I'm going to erase that. So I'm just going to pull out a 4, and we're going to make this 2 square root of negative lambda. It would still be 4. You're right. I don't know why I wrote 2. And we're going to have our plus or minus. Because this is the same thing as the square root of 16 and the square root of negative lambda. So the square root of 16 turns into positive 4, and we have square root of negative lambda. Now I'm going to do the same steps and get up to that same point with my t's, in which case I'll have m squared plus lambda is equal to 0, which gives me m squared is equal to negative lambda, which tells me that m is equal to plus or minus the square root of negative lambda. So now right now you're looking at me and you're probably saying, okay, this looks like it's going to be 2 eigenvalue problems. But one thing to notice that I'm noticing right now is that we have this same square root of negative lambda in both of them. So if we solve for what the square root of negative lambda is in one of them, this is the same value lambda. Just because it's written in 2 different places doesn't mean it's different. It started off right here, which was the same for both our x's and our t's. So if I find my value of lambda for this one, and I choose this one because it's a little bit simpler than that. If I find my value of lambda for this one, I know that it's going to be true for this one as well. Make sense? So we're going to go through and start our eigenvalue with this one. No, I'll do case 1 right here. So we're going to start off with our case 1. And in case 1, I'm going to say that this negative lambda is equal to 0, which means that my m is going to be equal to plus or minus 0, which means that my solution is going to be capital T is equal to C1 plus C2 times T. The one thing that's very nice about eigenvalue problems is once you solve for your m, all of your cases end up being the exact same thing, just plugging in different boundary conditions. Because I'm always going to, if my lambda is equal to 0, I'm always going to get this form for my case 1. So I have T is equal to C1 plus C2T. I'm not going to be able to do this way. So what I'm looking at right now is my boundary conditions are given in terms of my x, which means I can't do my solving for my t's. I gotta do my solving for my x's. because what I'm getting at is the next step that I would do for that is I would take the derivative, I would plug in my boundary conditions, and I would solve for my C1 and C2. But my boundary conditions give me values for x. So I have to use my x to figure out those boundary conditions. I can't do my t.
Could we just put the 16 with the t then?
I believe it would end up being 1 over 16. So I'm just going to leave it here. And it's just going to stay out front. And to be honest, it's not going to, because we're still looking at the negative lambda, it's not going to matter. That 4 is just going to come into play at the end. So, now looking at case 1, I'll rewrite it over here so we're not confused. We have case 1, and again, I'm still looking at the stuff underneath my square root. So case 1, I'm still saying that negative lambda is equal to 0, which means that my m is going to be equal to plus or minus 4 times the square root of 0, which means that m is still going to be 0. Nothing different. Which means that capital X is going to be C1 plus C2X. Now, looking at my boundary conditions, I have 1 for just my x, and I have 1 for x prime. So I'm going to take the derivative of this, which just gives me x prime is equal to C2. So I'm going to plug in my first boundary condition right here, where I plug in 0 for x, 0 for capital X, and 0 for lowercase x. And this gives me C1 equal to 0. Come over here to my second boundary condition, where I have u sub x of 1 and t is equal to 0. So I plug in 0 for my capital X prime. I don't even have a little x to plug in 1, so I just get 0 is equal to C2. So C1 is equal to 0, C2 is equal to 0. I can write no eigenvalues. And in my case 1, I get nothing. I'm going to do this. Move over here. So now we're on to our case 2. And in my case 2, I'm saying that everything underneath the square root is going to be positive. So this negative lambda is going to be greater than 0, which means negative lambda is equal to alpha squared. So if negative lambda is equal to alpha squared, then I know that my m is equal to plus or minus 4 times the square root of alpha squared, which means m is going to be equal to plus or minus 4 alpha. Now this is a little bit different than what we're used to seeing. We're used to having just plus or minus alpha. But we're just following the same steps that we normally do. Substitute for our lambda, solve it, and we have plus or minus 4 alpha. So I know that in my case 2, I have real non-repeating roots. So I know that my solution, following the same steps that I did in the last problem, I have capital X is going to be equal to C1 e to the 4 alpha times lowercase x plus C2 e to the negative 4 alpha lowercase x. And again, I'm going to take the derivative. So I'm going to have capital X prime is equal to, and in this case we're going to have 4 alpha C1 e to the 4 alpha x minus 4 alpha C2 e to the negative 4 alpha lowercase x. So now that I have my function for x and I have my derivative, I can plug in my boundary conditions again. So to this one, it says that when x is equal to 0, my capital X is also equal to 0. So I have 0 is equal to C1 e to the 0 plus C2 e to the 0. And this just gives me that C1 is equal to negative C2. Take that and I bring it up here for my second condition, which is when my capital X is equal to 0, my lowercase x is 1. So I have 0 is equal to 4 alpha C1 e to the 4 alpha times 1 minus 4 alpha, and then for C2 I'm going to plug in negative C1, so I'm going to make this plus 4 alpha C1 e to the negative 4 alpha, and again times 1. So now I'm going to move one of these over to the other side. We have negative 4 alpha C1 e to the 4 alpha is equal to 4 alpha C1 e to the negative 4 alpha. And just like you're used to doing in your case 2, we'll divide out these 4's, we'll divide out the alphas, divide out the C1's, and we get negative e to the 4 alpha is equal to e to the negative 4 alpha, which is not true. No eigenvalues, once again. Shocker. And now for the fun part. What if our negative lambda, so we got case 3, what if our negative lambda were less than 0? So negative lambda is equal to negative alpha squared. Well, in that case, I'm going to have my m equal to plus or minus 4 times the square root of negative alpha squared, which means m is equal to plus or minus 4 times alpha I. Continuing on, we get our capital X is equal to e still to the 0x, because I still have a 0 in front of this plus or minus. So I get e to the 0x times C1 cosine of now 4 alpha x plus C2 sine of 4 alpha x. The only difference with this 4 is we just carry the 4 inside of these sine and cosine. So now, just like in the last two cases, I'm going to take the derivative of this, where my e to the 0x can just become 1. So I'm going to have capital X prime is equal to, from this first term, we're going to get negative 4 alpha C1 sine of 4 alpha x. And this second term, we're going to get positive 4 alpha C2 cosine of 4 alpha x. Plug in the boundary conditions. My first boundary condition, I plug in 0 for lowercase x and 0 for capital X. So 0 is equal to C1 cosine of 0 plus C2 sine of 0. I know that sine of 0 is 0. I know that cosine of 0 is 1, so I get C1 equals 0. I come over here, my whole C1 term, I'm just going to cross off right away because I know C1 is equal to 0. Then for x prime, I plug in 0, and then I'm going to plug in 1 for my lowercase x. So I have 4 alpha C2 cosine of 4 alpha times 1, and we're here. This is actually turning out to be very similar to the last problem. Because I know 4 can't be 0 because they're different numbers. I know that alpha can't be 0 because then I would be back in case 1. I don't want C2 to be 0, so that means that 0 has to equal cosine of 4 alpha. So now in the last problem we had sine of 4 alpha, and we knew that that was n pi. This time we have cosine of 4 alpha, so we need to figure out at what values on our unit circle is my cosine equal to 0. Well, I know that my cosine is my x value. So I hit that when I'm right here at an angle of pi over 2. And then I keep moving around the circle, and I get this point, which is 3 pi over 2. And then 5 pi over 2, and 7 pi over 2. And I keep going around the circle. And the pattern that I end up getting is that I need to have a cosine of some odd number times pi over 2. And the way that we represent that odd number is just with 2n plus 1 or 2n minus 1. So we have cosine of 2n plus 1 pi over 2. Make sense? Cool. So therefore I know that if cosine of 2n plus 1 pi over 2 is equal to 0, then I can take this 4 alpha that I have right here and set it equal to 2n plus 1 times pi over 2. And if I want to figure out what alpha is, just divide this 4, and I have my alpha. 4 n is equal to 0, 1, 2, and so on. Not much different from the last problem yet. A lot of the same steps. We just had an extra 4 hanging along, but that could happen in the first problem too. So now we're at this point. We want to, again, figure out what our lambda is. So I want to get back to our lambda, which means that negative lambda is going to equal negative 2n plus 1 pi over 8 squared. And I can just drop the negatives out in front. And I have my lambda sub n is equal to 2n plus 1 times pi over 8, all that squared. For n is equal to 0, 1, 2, and so on. Make sense? So what's the next step that I want to do? I now have my eigenvalues. What do I want to find? Someone's going to say it. Eigenfunctions. There we go. So I know that right here is my function. That is the answer in case 3. I also know that I can ignore this whole first term because C1 is equal to 0. So I can write my eigenfunctions as capital X sub n is equal to this C2, which I'm now going to write as C sub n, times sine of 4 times alpha, where alpha is this whole thing, so I'm just going to multiply this 4 in, put it back over 2, and we're going to have 2n plus 1 times pi over 2, and then bring that x along. And don't forget the 4, n equals 0, 1, 2, dot, dot, dot. Because they'll probably take off a point if you don't write that. So now all this nice bunch of cases was just so that way we could answer our function for x. We still don't know anything about our function for t. Yes?
Do we need to account for the 4 before the alpha and x?
So I did. I kind of skipped it. I multiplied the 4 in here. So when we have 4 over 8, it just becomes over 2.
Gotcha.
So you might be looking at that t and saying, I now have to do a whole other set of eigenvalues for that. But you don't, because these eigenvalues that we found apply to that one as well, which is nice. Saves us some time. So what that means is I now need to write out this solution, because I need an equation for t. Just like I have this x sub n, I need an equation t sub n. So what I can kind of do is, I know that when I solved case 1, I got nothing. When I solved case 2, I got nothing. So I know that the only answer the only situation that's going to give me an answer is my case 3. Which means that I know my answer is going to be in the form of my imaginary solutions. Because I know that this stuff is going to be negative. So here's how I'm going to do this. I'm going to say that my negative lambda is going to be less than 0, which means my negative lambda is going to be equal to negative alpha squared. And if that's true, then that means my m is going to be equal to plus or minus alpha I. I can take this plus or minus alpha I, write out the form of my answer, which is going to be capital T, change colors. So we have capital T is equal to, again, it's going to be e to the 0t times C1 cosine of alpha t plus C2 sine of alpha t. And this alpha, this alpha is the same exact thing as that alpha. Because notice, we know that this lambda is the same exact thing as that lambda. And we said that negative lambda is equal to negative alpha squared. Negative lambda is equal to negative alpha squared. So therefore, this alpha is the same thing as this alpha that we solved for. So I can take that and plug it in right in here. So I can say that I have t is equal to C1 cosine of 2n plus 1 pi over 8 times t plus C2 sine of 2n plus 1 pi over 8 times t. Is this making sense, hopefully? So now what this gives me is a t sub n for n is equal to 1, 2, 3, dot, dot, dot. Yes?
What do you do with the constants?
That's in the next step. You'll be, I'm glad someone asked that. They're going to go away in a pleasant way. Yes?
So how come sometimes we say like on that side we did n equals 0, 1, 2, and then here we're doing n equals 1, 2, 3?
This should be 0, 1, 2. And basically, in most problems, such as this one, you can choose if you want to start at 0 or 1. All that matters is if you do 2n plus 1, then you can start at 0, because if I plug in 0, I get 1. If I do 2n minus 1 to represent my odd number, and I start at 0, then my first answer is negative, and we want to try to avoid that. So if you're a person that likes to do 2n minus 1, just start your n at 1, 2, 3, 4, so on. But in your eigenvalue problems, it doesn't matter so much.
If we lose points during the exam, if we didn't put alpha, we just left solving everything?
If you can want to solve this just using your lambda, you can do that. If you know how to do it and you feel comfortable doing it, then go right ahead. You don't have to use this alpha. It's just one method that you can use to solve the problem.
Once you go back to the t's, if you don't do the first two cases, will you be taken off?
No, because you already did the first two cases. You just did it in the x situation. And you know that there's no answers in those situations.
So the reason we did the t is because of the third initial condition. Why do we have to do case 3?
Because the only case that we got an answer for our x's was for case 3.
We could just say like go straight to case 3.
You can't do that for your x's, but for your t's you can do that. And here's the reason. So when we solved case 1, which was right here, we got c1 is equal to 0, c2 is equal to 0. If we were to take that c1, 0, c2, 0, and we multiply it by this that we got here, we're just multiplying this by 0 and we get nothing. So therefore, in the case 1 option of t, we would have nothing. When we solve case 2, we got no eigenvalues, which is the same thing as saying c1 is equal to 0, c2 is equal to 0. So if we were to take that 0 value for your function of x, and you multiply it, your x times t to get your u, again, you would just be left with u equals 0. So we know that case 2 means nothing for our t's. So the only answer that we got for our x's was in case 3. So the only answer for the entire problem is going to be in case 3, which is why we can go right to case 3 for here. Does that make sense? Because we know that in this entire problem, we're trying to find function u, which is just capital T times capital X. So if we know that x is 0, t doesn't matter, because you're multiplying 0 times something, it's just 0. So now we're at the point where we have a function for our t, and we have a function for our x. And what we did in the last problem, when we had those two, was we put them together. So let's do that. So I can now write out u as a function of x and t is going to be equal to c sub n sine of 2n plus 1 times pi over 2x. And now I'm going to multiply this whole thing by both of these terms. And the c sub n, where do I want to do this c sub n? Instead of writing this c sub n out here, I'm going to write it, because it's going to get distributed to both of these terms. So I'm just going to write it inside of my parentheses. So we're going to have it written like this. U of x t is equal to, I'm going to write it as c n times the first term, which is cosine of 2n plus 1 pi over 8t and then plus, and this is going to be a different c sub n, so I'm going to write it as, I don't know the proper notation, but I'm going to write it as c sub n2. That's probably confusing. I don't know the proper notation, but because this constant is going to be a different thing from this constant, but it still depends upon what your n is. So it's still based on n, it's just a different one, so I'm writing it as c sub n2. Hopefully that's not too confusing. So we have c sub n2 sine of 2n plus 1 times pi over 8t. Does this make sense what we have right now? I understand that this second c sub n is probably a little confusing, but other than that, does it make sense? We just multiplied our x times our function of t that we found over there. Yes. So this c sub n, I just multiplied by c sub 1 and c sub 2 to get c sub n and c sub n2. Okay. So now, going back to the question of, we need to figure out what these c's are. And notice how right now in the last problem we had one c that we needed to figure out, and we had one initial condition. Now we have two c's, so we have two initial conditions. So the first thing that I'm going to do is I'm going to take the derivative and I'm going to plug in this one, because it's probably going to tell me that either this c sub n or c sub n2 is going to be 0, and then I can just ignore it for plugging in the other condition. So I'm going to take the derivative of this whole thing with respect to t, which means this first term can just stay by itself. So I'm just going to rewrite that. So we have u of xt, or sorry, u sub t, because we're taking the derivative with respect to t, is going to be equal to sine of 2n plus 1 times pi over 2x and now we get to take the derivative of this, which is going to be fun. So I know that this c sub n is going to stay. Cosine is going to turn into a negative sine of 2n plus 1 times pi over 8t. And then I know that I have to divide, or I have to multiply by that term, this 2n plus 1 pi over 8. So I'm going to bring that out in front. And this is because of the chain rule. And then I'm going to take the derivative of the second term, which is going to give me the same thing with the 2n plus 1 pi over 8 times c sub n2 cosine of 2n plus 1 pi over 8t. I know it's a lot of terms and it's going to get a little bit confusing, but if you just keep in your head that this whole 2n plus 1 pi over 8 is just a constant, just treat it like a constant. So that's why it gets multiplied out in front. So what this initial condition here is telling me is that I can plug in 0 for t, and I get 0 as my answer. So I'm going to have 0 is equal to this first term with x's. I'm leaving x in there, so we know that this isn't going to be equal to 0. So I'm just going to kind of leave a placeholder for it. But now I'm plugging in 0 for t, which when I plug in 0 for t here, I'm going to have this. Negative 2n plus 1 pi over 8 c sub n sine of 0 plus 2n plus 1 pi over 8 c sub n2 cosine of 0. Too many parentheses. Not enough parentheses. So I know that I have sine of 0 here. So sine of 0 is 0, so that whole term goes away. So I know that this term right here needs to be equal to 0. And I have cosine of 0 is equal to 1. So now rewriting all of this, I'm going to have 0 is equal to 2n plus 1 pi over 8 times cn2. And I know that pi isn't 0, and this 2n plus 1 can never be 0 because this n can only be 0, 1, 2, 3, 4. So therefore, cn2 has to be 0.
Why are you ignoring the sign of 2n plus 1?
Because I know that what this is saying is I'm plugging in x for it. So I know that when I plug in x here, it's just staying the same.
Okay.
So I know that this isn't going to be 0. So I know that this side has to be 0, which leads me to that cn2 is 0. So what that lets me do is I can say that this cn2 up here is 0, and I can cross this out. Erase this part. So now I have my first constant, my first coefficient solved for with that cn2. The last thing that I need to figure out is what is that cn? And for that, I'm going to plug in that first initial condition that's written. So I'm going to have u of xt, I'm just rewriting what I have on the top line over there, is equal to sine of 2n plus 1 pi over 2 x all times c sub n cosine of 2n plus 1 pi over 8t. So now I look at that top initial condition, and that tells me that when I plug in 0 for t, I'm going to get negative 6 sine of 3 pi over 2 plus 13, or 3 pi over 2x plus 13 sine of 11 pi over 2x. So I'm going to do that. I'm going to have 0, or u is equal of x, and 0 is equal to sine of 2n plus 1 pi over 2x. And when I plug in 0 for this t, I'm just going to have cosine of 0. And the cosine of 0 is just going to be 1. So this is just going to be a c sub n. And now hopefully this looks kind of familiar to where we ended up in the last problem, where now we have a c sub n sine of 2n plus 1 times pi over 2x is equal to that thing, -6 sine of 3 pi over 2x plus 13 sine of 11 pi over 2x. And does anybody remember what we did at this point in the last problem? Find our value for n, right? I know everyone was thinking that. So that's what we're going to do. Looking at this right here, what can I plug in for n that gets me 3 pi over 2? 1. If I plug in n equals 1, it's going to give me 2 plus 1 pi over 2. So this is n equals 1, this term. And therefore my c sub 1 is -6. Now I do the next one. And what do I need to plug in for n to give me 11 on the top? 5. Which means that c sub 5 is going to be 13. Now I just figured out what my second c is. So we get to take everything that we just found, plug it into this purple equation that we got, and we're going to have a final answer. So we get u of x and t is equal to sine of, oh wow, this is going to be really freaking long. So the first one is going to be when n equals 1. Yeah, we're gonna need this whole board. So when n equals 1, we have sine of n equals 1, so we get 3 pi over 2x. This cn is going to be -6, so I'll bring that out all the way in front. So we have the -6 sine of 3 pi over 2x times cosine of 3 pi over 8t. This is all our n equals 1 term. And now we need to do our n equals 5 term. So we're going to get sine of 11 pi over 2 times x. Our c sub n is going to be 13, so I'll bring that out in front. And we're going to have cosine of 11 pi over 2t. And this is our n equals 5 term. And this is our solution to the wave equation with those boundary conditions and those initial values. Question? Yes, it should be. It should be 11 pi over 8. I just got excited. Did I mess anything else up?